So this time we're going to find the electric field due to an infinite plane of charge. Suppose this is the the plane, the sheet of charge, and it is positively charged. All electric fields must be perpendicular to this plane of charge, right? There's electric field at this direction, perpendicular to this plane. There's also electric field going that direction, which is also perpendicular. Since this sheet has two sides, so there is electric field going that direction, and there's also electric field going at that direction. Now, all points that are equidistant from this plane of charge must feel this the same magnitude of electric field. Alright? So what is the best Gaussian surface we can use to determine the electric field? Since the charge are uniformly distributed in this plane of charge, so meaning it is symmetric. So the best Gaussian surface we can use to obtain the electric field to this plane of charge is small cylinder. Now, if this is the Gaussian surface, the cylindrical symmetry is the Gaussian surface, is what we call the imaginary surface. The axis of this cylinder must be perpendicular. So this is the axis of the cylinder, perpendicular to the plane of charge, right? Since electric field is going at that direction and perpendicular to this surface, so the electric field is also perpendicular to the surface of this cylinder, but parallel to the curved surface of this cylinder. So meaning this surface of the cylinder has no contribution to the integral area, surface area. So since there are two sides of this plane of sheet of charge, electric field goes at that direction as well at this direction. So meaning the electric field penetrates two areas. One area at this side, and one area at this side. So the total area, the surface integral, is 2 times the area. So the total flux to each end is the dot product of the electric field and the area element. So we have the total flux 2 times the electric field, that the total area. Now suppose this is the plane of sheet, there is cylinder, electric fields are perpendicular to this plane of sheet as well as the base of the cylinder, and then electric field passes through two area, one at the side and one at the side, and both electric fields are both perpendicular to these two areas. And then the surface, this plane of sheet has the surface charge density or areal density, charge density, and the charge density can be obtained by the net charge or charge per unit area. So how can we obtain the electric field of this plane of sheet? This is the side view of the sheet plane of charge, and then we're going to use the cylindrical symmetry as the Gaussian surface, since the charge are distributed uniformly on the plane of charge. Alright. The electric field is perpendicular to the plane of charge, as well as the base of the cylinder. Since there are two sides of the plane of charge has two sides, then there's electric field going that direction. There's also electric field going that direction. So there are two surface area where the electric field will penetrate. One area is this one, and one area is this one. But the curved surface of this cylinder has no contribution to the integral surface area. Why? Because the area vector for this surface, the curved surface of the cylinder, is perpendicular to this surface, and it is perpendicular to the electric field, direction of the electric field. So cosine of 90 is 0. So meaning this surface area again has no contribution to the integral surface area. So we'll use again Gauss's law to obtain the electric field due to this plane of charge. So from Gauss's law, the total flux, which is equal to the closed integral of the electric field, that the derivative of the area vector is equal to the net charge Q of O over permittivity of free space. This is Gauss's law. Right. So the total integral surface area is twice of these areas. There are two areas here. This area and this area. So 2 times the area. This is one area and another area. These two areas have the same magnitude. So we have the electric field times 2 times the area, which is equal to the charge over permittivity of free space. And we know that the surface charge density is the charge per area. So the charge is the charge density, surface charge density times the area. So electric field times 2 times the area must be equal to, I will replace charge by surface charge density times the area. So we have surface charge density times the area over permittivity of free space. So I can cancel area. Then we have electric field equals the surface charge density over 2 times the permittivity of free space. And we know that the permittivity of free space is 1 over 4 pi times Coulomb's constant. So I will replace permittivity of free space, because usually Coulomb's constant is used to find the electric field, not the permittivity of free space. So I will replace permittivity of free space by 1 over 4 pi Coulomb's constant. So we have electric field equals the surface charge density over 2 times 1 over 4 pi Coulomb's constant, or the electric field equals 4 pi K times the surface charge density over 2. So I will cancel 2, and then 4 becomes 2. 4 divided by 2 is 2. So meaning the electric field is 2 times pi, 2 pi, that's Coulomb's constant, and surface charge density. So this is how we determine the electric field due to an infinite plane of charge. 2 times pi times Coulomb's constant times surface charge density.